Okay, we're going to continue on here, chapter 14. We're going to talk a little bit about liquids and solids in this chapter. So let us get into it. So a little bit about water. Water, obviously, as we know, is colorless, tasteless substance. At 1 atmosphere of pressure, it will form a solid. That's the normal freezing point of water. That's also obviously the normal, not boiling point, normal melting point as well. Speaking of boiling point, that is 100 degrees Celsius. Remember that at these temperatures of 0 degrees Celsius, for example, you do have both phases in equilibrium with each other. So at exactly 0 degrees Celsius, you have really both solid and liquid sort of happening at the same time. It's kind of like ice crystals. As we'll talk about, it's not really until you get a little bit above 0 degrees that you sort of fully transition into liquid water. Not until you get a little below 0 degrees that you're kind of in ice. And same thing at the boiling point as well. At exactly 100 degrees Celsius, you have both of those sort of phases occurring. You have liquid and gas happening at the same time. And again, it's not to really get just above 100 degrees Celsius that you transition into gas, or below, obviously, you're in liquid. It is liquid water between 0 and 100 degrees Celsius. Water does expand when it freezes, and one of the reasons for that is it's one of unusual substances, and the fact that actually water in its solid phase, or ice, is actually less dense than water in the liquid phase. And that has a lot to do with the bonding that occurs with water and other water molecules. So as the water molecules bond together between, say, the oxygen and the hydrogen here, and as they come together in the solid phase, which is obviously our ice, what ends up happening is it creates a lot of really kind of open spaces between the water molecules. So there's a lot of open sort of volume between all these water molecules. And if you think about sort of density, which is mass divided by volume, what happens in sort of the solid state is, because they don't have enough energy, they actually keep a fairly good distance between each of the water molecules. And that increases the overall volume of ice. And what that does is it will bring the density down. And that's different than in the liquid phase. In the liquid phase, water has a little bit more energy, which means those water molecules actually can get a little bit closer to one another. It doesn't create as much kind of open space between the water molecules, and thus we have a little higher density there in liquid water than in ice. That's why, again, when we put ice in our drinks, right, it floats to the top usually. And again, because it is less dense. Obviously, they do want you to know really the density of water, and that's the density of liquid water, which is 1 gram per milliliter. Density does change with temperature, and but I would say probably in 99.9% of the time, if you ever find yourself in a problem or anything like that where you need the density of liquid water, probably 1 gram per milliliter is probably the best choice to use. But it actually does change with actually temperature as well, density. This is a heating and cooling curve, and going from ice, which is our solid, to obviously here liquid in the middle here, water, and above here steam, which is really our gas phase. And this is what we see for water, obviously going in this direction here, we are heating. So we're actually an endothermic type process occurring here, right? So you got to put heat and energy in to do that as you're heating it up. Thank you. If we have like our ice cube, it'll pick up some heat and energy, start to melt. If you have liquid water and you put some fire underneath it, right, adding some energy to it, it will start to boil and create steam. Vice versa, going backwards from gas to liquid to solid, those are exothermic processes. And that is the cooling part of it, which is exothermic. heat and energy needs to be released. So in the gas phase, as these gas molecules are flying around with a lot of energy, as you release that energy, they slow down and they kind of stick to each other. They can't really escape each other when they hit each other, and they fall like into the liquid state. As they lose more energy, they kind of slow down and kind of lock into the solid state at that point. And again, that's the release of energy as we kind of go in the opposite direction. And again, going obviously in the first direction there, as we talked about, is endothermic. Remember that when we talk about exothermic and endothermic in terms of energy, endothermic energy values are typically positive values, right? Like delta H, which is our change in enthalpy, are negative for exothermic, like our delta H is negative in this particular case. So let's talk a little bit about the energy to change state. And there is actually a certain amount of energy required to do really nothing more than change the state of a substance, not change the temperature or anything like that. Again, the change of a state occurs at, for example, the normal melting point or freezing point or the normal boiling point. And there's a certain amount of energy required just to simply do that step. The molar heat of fusion, which is sometimes referred to as the delta H of fusion, for water here is 6.02 kilojoules per mole. That is roughly there. Do a quick conversion there. About 334 joules per gram. And that's how much energy is required to basically change liquid water to ice or ice to liquid water at 0 degrees Celsius. This is where it occurs. This occurs for water at 0 degrees Celsius for water. That again is his normal sort of freezing point, melting point where that occurs. There's also a certain amount of energy associated with the transition of going from liquid to gas or gas to liquid at the normal boiling point. And once again, for water here, that's 100 degrees Celsius is normal boiling point. And that is the delta H of vaporization. So the delta H of vaporization is the heat required to do that transition. Again, we're not really changing temperature. We're just really changing the state of a substance. For water, it's about 40.6 kilojoules per mole, or roughly 2260 joules per gram, give or take. So this is the energy, like I said, required basically to do that transition at the melting point or the boiling point, depending on which one you're at. So when we look at this, this is where we're talking about. So for water here, we're talking about this transition right here at 0 degrees Celsius. That would be our delta H of fusion that we would use. And here as well, again, you can see it's plateaued out, which means the temperature does not change, but we do change the state. And that is the delta H of vaporization there that you would use to do that transition. Now, you can also see from the graph here and also from the numbers that we just saw, it does take a lot more energy to do the transition from liquid to gas than it does going from solid to liquid. And if you just think about it, as you go from solid to liquid, in the solid state, things are packed in pretty tight to each other. In the liquid state, they're still relatively packed in pretty tight to each other. They have a little bit more energy for movement. But as you transition from the liquid state, where again, there's a little bit more room, to the gas state, at that point, everybody has basically broken apart from one another. So they're definitely moving around a lot more distance. So it takes a lot more energy to do that transition, as you can kind of see based on just the length of the lines here versus this line and this line. Now, when we look at something like this, as we go from solid to liquid, that is an endothermic process, which means that this energy value here, or the heat of fusion, will be a positive, for example, for water, 334 joules per gram. We'll just use that number. But again, if we were going from liquid back to solid, that is an exothermic process, which means that the number will be the same, but our sign would be different. It would be negative 334 joules per gram. So again, it's the same amount of energy regardless of which way you're going, but the sign will change depending on sort of the process that's occurring. Is it exothermic or endothermic? Same thing with our heat of vaporization as we go from liquid to gas. That's an endothermic process, which means our heat of vaporization would be a positive 2260 joules per gram. Or if we're going back the other way from from gas to liquid, that is an exothermic process, which means it would be negative 2260 joules per gram. Also, if you want to use the mole version there, 602 kilojoules per mole, bless you, or negative 6.02 kilojoules per mole. And obviously this would be positive 40.6. And this would be negative 40.6 kilojoules per mole. So again, much like we talked about when we talked about energy and definitely specific heat, we do want to make sure that if something is negative, that we don't ignore the negative sign, because again, it tells people what type of process is occurring. Is it exothermic or endothermic? Questions on that there? So when we look at this heating curve and we look at the different points on it, obviously the ones in boxes we use are heat of fusion, heat of vaporization. Again, there is no change in the temperature as we do those transitions. It occurs at the exact same temperature. It just depends on what you're doing, putting energy in or out. But if we look at the rest of the sort of curve here, we actually do see a couple of things, which is down here, this is all solid and it is changing temperature. So everywhere through there where I just highlighted green is in the solid state, but the temperature is changing. Everywhere here as well is in the liquid state and the temperature is changing. And everything here is in the gas state and the temperature is changing. So when we deal with something where the temperature changes but the state does not, we actually use an equation from our past to figure out the energy and heat associated with it. And that is our friend, the specific heat equation we used way back when. And if you remember, that is Q is equal to ms delta T, Q being heat, right, or energy. That's joules or calories. M is mass, which is in grams. S is our specific heat capacity. And that's the one that has those 3 units, joules per gram per degree Celsius, or calories per gram per degree Celsius. And remember the importance of the change in temperature. We always want to do final temperature minus initial temperature. So always final minus initial. And that is one of the few things in chemistry that actually we don't convert to Kelvin. We do leave it in degrees Celsius because the specific heat capacities are typically given to us in degrees Celsius. You should also remember, yeah. Because there's a certain amount of energy required to actually just change the state of it, but it's not enough to get the temperature basically to move, basically. So until you get enough energy to fully make that transition at that point. So what happens at these processes is the system's in equilibrium with each other. There's kind of equal amounts, if you will. Not really equal amounts, but the rate of kind of the ice and the liquid water is the same, making and breaking basically ice and liquid water. And at that temperature is not enough to pull that equilibrium one way or the other. So it kind of just stays right there. It's not enough to move temperature to cause it to go, all the way to ice or cause it to go to liquid water. So there's enough energy to change the state of the substance, but not enough to move basically the temperature of it. And if you are able to move the temperature of it, that's enough to cause that equilibrium not to happen. and cause it to go one way or the other, and it'll cause it to either go all the way to ice. Like, for example, if you removed enough energy at that point at 0 degrees, what will happen is you will start to see basically the temperature change and then fully transition to ice. Or if you added enough energy, you'll see everybody go the other way and go towards liquid water at that point. Other questions? So a reminder, that couple of numbers, right, that they do want you to know, which is the specific heat capacity of liquid water, and that is at 4.184 joules per gram per degree Celsius number. Or if you're using calories, that is 1 calorie per gram per degree Celsius. By the way, that again is the conversion, as we talked about, between calories and joules. 1 calorie is 4.184 joules. So that is those conversions. Remember, it's important, especially in a situation like we're dealing with here, it's important to understand that the substance phase is actually important. For example, if you were using our specific heat equation here, and you're down over here at ice, ice has a different specific heat capacity than liquid water. It's more like 2.03 joules per gram per degree Celsius. Same thing if you were using the specific heat equation in this region. The steam has more like a 2 joules per gram per degree Celsius as specific heat. So that 4.184 joules per gram per degree Celsius is specific for liquid water. And if you happen to be above 100 degrees, which would be steam, it's not liquid water, or below 0 degrees, it would be ice, which is not liquid water, then you do want to make sure you use a different value for the specific heat capacity. So if we were doing some type of calculation, like we'll do this one here in just a second, anywhere on this sort of graph that we are going upwards, if you will, where the temperature is changing but the state is staying the same, you would want to calculate the heat or energy with the specific heat equation. Anywhere where you're at the sort of those transition points where basically the temperature stays the same, but the phase changes, that is where you would want to incorporate either the heat of fusion if you're doing that transition, or the heat of vaporization if you're doing that transition. The total amount of energy to do something is we basically could just add all the different parts of it together. So, if we started way down here and we want to figure out how much energy to get way up here, which is what this problem is, we basically just want to break it up into parts and figure out how much energy to do each of those parts, and then add up all the energy at the end. Any questions on that there? So why don't we actually do this problem here that I just kind of scribbled all over here. So let me erase all that there. All right, so let's take a look at this problem, which is we want to know how much energy is required to change basically 75 grams of ice that's starting at minus 3.5 degrees Celsius to steam at 102 degrees Celsius. So essentially we are going to start over here. So that's kind of where we're going to start. And we are going to end basically over here. And we want to figure out how much energy is required basically to do that. So we do want to kind of break it up by kind of parts that's going to happen. So the first thing that's going to sort of happen is we are going to go from our starting point basically to 0 degrees Celsius. So that's basically our very first sort of step there, which is we need to take our ice that's at minus 3.5 degrees Celsius and take it to ice at 0 degrees Celsius. So step number 1 is going from ice at minus 3.5 degrees Celsius to ice at 0 degrees Celsius. And that is basically the same phase, but different temperatures. So we would want to use our specific heat equation to do so. Again, if you look at the graph, we're going upwards on that graph. So in this case, our Q would equal our mass, which was 75 grams. Again, here we would want to use the specific heat capacity of ice And I'm going to go with it being, I think it's 2.03, give or take, pretty close. We'll go with that. And again, here we would not want to use that 4.184 number because we are not at liquid water yet. So we're still at ice, so we need to use the specific heat capacity of ice. So we'll go with 2.03 joules per gram per degree Celsius. Here we want to do our final temperature, which in this case is 0, minus our initial temperature, which is negative 3.5 degrees Celsius. And here we will end up with 75 times 2.03 times basically 3.5. That's going to give us something like 532.9 joules of energy. That is the energy basically to take our ice that started at minus 3.5 degrees up to ice at 0 degrees Celsius. We ended up with a positive number, which makes sense, right? Because we're basically melting our ice, right? We're trying to melt it. So we got to put energy in there. So it should be positive and endothermic. That brings us, if we kind of look at our graph, right here to 0 degrees Celsius. And what happens at this point is we actually have a phase change, because this is where water normally will change phases from solid to liquid, and we're at 0 degrees. So this is actually the second thing that we need to do, which is simply change our ice that's sitting at 0 degrees to liquid water at 0 degrees. So that is just a phase change. We are not changing the temperature, we're just changing the state of it. So at this point, we're going to take ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. So once again, this is a phase change. The temperature stays the same. This is our transition from solid to liquid, and that is our delta H of fusion that we want to use. And there's those two numbers, the 6.02 kilojoules per mole are the roughly 334 joules per gram. I'm personally going to use this number, and that's because my other number's in joules. That way everybody's in the same units, and everything should cancel out correctly. I don't have to calculate moles or anything like that. So to do this, all we simply are going to do is take the mass of our ice, which is still 75 grams. We're going to use that heat of fusion, 334 joules per gram. The grams are going to cancel each other out, and we will end up with about 25,050 joules. So that is the amount of energy required to take my ice at 0 degrees and then basically turn it into water at 0 degrees, basically the amount of energy needed to do that, to be put into the ice to get it to basically melt into liquid water at that point. Any questions on that so far? So we're almost there. We have now transitioned here, and now we are sitting right about here. We're sitting at liquid water at 0 degrees. Our next really sort of process is we need to take our liquid water at 0 degrees, and we basically need to take it all the way up to liquid water at 100 degrees, as that's our next sort of transition that's going to occur. So we would want to go from there all the way to here, and this would be our third step. This again is everywhere in that blue line that I just highlighted. That is all liquid water all the way through there, which means it's the same phase all the way through, but definitely the temperature is changing as we go all the way through there. So again, anytime where the phase stays the same and the temperature is changing, that again is our specific heat capacity equation. So we will do that. We're going to now take it from liquid water at 0 degrees Celsius to liquid water at 100 degrees Celsius. So that's going to be our Q is equal to ms delta T. We still have our 75 grams now of liquid water. because we have now transitioned to liquid water, we do want to now use the specific heat capacity for liquid water, which is that 4.184 joules per gram per degree Celsius. Here again, we want to do our final temperature, which is 100, minus our initial, which is 0. And that's going to get us here about 31,380 joules. So we have now taken basically our ice from ice to ice at 0. We transition at 0 degrees ice to 0 degrees liquid water. We have now boiled basically our liquid water all the way up to the boiling point of 100 degrees Celsius. It's at this point that it's now going to do another transition of phases. At its normal boiling point now, it's going to go from basically liquid water at 100 degrees to steam or gas, basically, right, at 100 degrees. So that is, again, our next transition that we're going to do, which is from here to here, basically. We're going to transition. And that would be our fourth step here. Once again, that is a flat line, which means the temperature is not changing, but the state is. And this is where our delta H of vaporization basically comes in. That again is the energy required to change liquid water to steam or gas at the boiling point. By the way, the delta H of fusion and the delta H of vaporization are specific for the substance. So you would not use these values that we're using here for some other substance other than water. So they would have their own heat of fusion, heat of vaporization type of values. So the fourth thing we're going to do is go from liquid water at 100 degrees Celsius to steam, basically, which is gas at 100 degrees Celsius. That is our delta H of vaporization, which is 40.6 kilojoules per mole, or about 2260 joules per gram. So I'm going to use, again, the 2260 as that is in joules, so everything will be in the same unit. I'm also going to flip the page, I think, here. So for number 4, we're going to take our 75 grams of liquid water at this point. We're going to use our 2260 joules per gram, which is our heat of vaporization. And we're going to multiply them here. And we're going to get 75 times 2260, about 169,500 joules of energy required to do that transition. As a side note, as what we talked about earlier, if we look at the transition here, which this is our delta H of fusion, it took about 25,000 joules to take ice to liquid water. It takes, as you can see here, about 170,000 joules to take liquid water to steam. So you can see a lot more energy is required to do that transition, just in comparison of those two sort of numbers. Now, we're very close now to the end here. We are sitting right now at steam at 100 degrees Celsius, but we do want to end up at 102 degrees Celsius. So we have one last small little transition, which we will go with that. Why not? That's going to take us right about to here. And that's going to take us from basically steam at 100 degrees to steam at 102 degrees. And that would be our final sort of step here to get to the end. So step number 5, we're going from steam at 100 degrees Celsius to steam at 102 degrees Celsius. Once again, here we're staying in the same state, but the temperature is changing. So that is going to be our specific heat equation that we want to use. And again, we have our 75 grams. We once again want to make sure that we actually use the specific heat capacity for steam and not liquid water here. So it's, again, somewhere around 2, we'll just go with 2 joules per gram per degree Celsius. So we'll do 2 joules per gram per degree Celsius. Again, our final temperature of 102 minus 100 going to get us here. So 102 minus 100 times 2 times 75. There you go. About 300 joules of energy is required to do that. Now, at this point, we circle all of our numbers here, there, and here, I think. If we want the total amount of energy required to go from where we started to basically where we ended, all we have to do basically is add up each of the parts that we did. So we always do simply to get our total energy, we add up basically the step 1 plus 2 plus 3 plus 4 plus 5 in this case. So we have 532.9. And since I did them all in joules, everybody's in the same units, which is good. 2505 joules. 31380. Then obviously we have 169, 500, and 300 joules. So the total amount of energy to do all of that transitioning is going to be here. About 2267, 62.9. Maybe we'll clean it up a little bit. We'll go about 227 kilojoules of energy is required basically to do all of those transitions. Question on any of those steps there? Yeah.
Well, we have a graph of that available, or do you memorize these state changes?
You probably should just memorize the state changes. It probably won't be included in a problem, basically, yeah. It's a similar sort of graph for most things. Again, you just got to think about transition points. As I mentioned before, the delta H of fusion or vaporization will change with the substance. Also, that will change with the substance will be its melting point, freezing point, boiling points will be different with different substances as well. By the way, what happens if we actually started up here and want to go this way and go in the opposite direction? What changes here? Yeah, everything's basically the same except that everything will turn negative, right? So if we were going in the opposite direction, these guys would switch around and we would end up with a negative number there. If we were doing the opposite direction, this guy here would be a negative 334, right? And that gives us a negative. Same thing here, these guys would switch around and that would give you a negative number for that. And obviously here, this guy would end up being negative, which would give you a negative number there. And obviously here as well, these would switch would give you a negative. So again, it would be the same amount of energy to go in the opposite direction, but that is an exothermic process, which means it would just basically end up being a negative number versus the positive number. Any questions on any of that there?
Whether you're going one direction or the other, it'll always be the same number.
Yeah, so it's the idea of what we talked about before, right? Is like it's really the same amount of energy, right? It's just kind of which direction it's going, right? So as we go from solid to liquid to gas, all that energy has to be put in, right? And to go in the opposite direction, you basically got to take all that energy you put in and take all that energy and take it out. So it's always the same amount of energy, kind of like when we talked about with specific heat, where we transfer energy, like say from the hot metal to the water, right? The amount of energy that the hot metal lost to the water is the same amount of energy that the water gained, right? That was that one where we did like the Q of the water equals minus Q of the metal, right? The only difference is the sign changes, yeah. Other questions? Yeah. It would, yeah. And then all the individual values that we got along the way would be negative as well, because you would do those kind of switches and then make the heat of fusion, the heat of vaporization negative as well. Yeah. All right. All right, then let's talk a little bit about intermolecular forces or intramolecular forces. So intramolecular forces are the forces within a molecule. So for example, if you took one water molecule by itself, this one water molecule is held together by covalent bonds, right? And that is sharing of electrons. And that is the intramolecular force, excuse me, there, which is basically those sharing of electrons between the oxygen and the hydrogen on the left and the oxygen and the hydrogen on the right. Also, in an ionic compound, if you have like a sodium and a chloride, the attractive force between those two guys are electrostatic attraction, right? Opposite attraction. And that's what holds together an ionic compound, right? Together with each other. They all come together and arrange their positive and negatives to bond to each other in a maximal attraction way. Now, that is different than an intermolecular force. Intermolecular forces are the forces that hold a molecule together with another molecule. And that would be, for example, if you took two water molecules. Water is polar, and that means that the oxygen side of water is more negative. The hydrogen side of water is more positive. And what happens is one negative side of one water is attracted to the positive side of another. That is an intermolecular force. That is the force that holds this entire molecule together with this entire molecule and keeps them together. It's the force that holds, for example, one molecule with itself. So like we have here two waters. It is also the force that holds a different molecules together as well. So it doesn't always have to be, for example, the same molecule, but a lot of times we do kind of look at the same molecules interacting with themselves. The intermolecular forces are always much weaker than the intramolecular forces. So intermolecular forces are always weaker than intramolecular forces. We know that because when we look at water as an example, and if we heat water up to like boil it, for example, what happens is this bond here, this intermolecular bond between the two different water molecules is actually the first one to break. And what that does is it allows this guy to go off into the gas phase, allows this guy to go off into the gas phase at that point and separate out from each other. If it was the opposite way and the intramolecular force was weaker than the intermolecular force, when you would go heat something like water, what would happen is these individual bonds in every water would break apart and you would produce a lot of hydrogen and oxygen gas really quickly and probably explode. So that doesn't really happen, right? So we're able to boil our water and make our pasta without any incident occurring. And that's because basically as we boil the water, we're breaking those intermolecular forces because that intramolecular force is pretty much the strongest force you could kind of have. Actually, that electrostatic attraction between the positive and negative attraction is probably the strongest intramolecular force that you could have. Covalent bonding is next, and then we have all these intermolecular forces. Yeah.
Just to verify that I understand correctly, the intramolecular force is like the force that holds, like for example, water, like H O H.
Yeah, it's the force that holds one single molecule together, basically. Yeah. So if you just took one single water molecule out, basically the force that holds that together is the covalent bonding, the sharing of electrons, those bonds between the oxygen and hydrogens. That's intramolecular forces. Intermolecular forces, when you get a bunch of waters together, how they basically bond to each other, the entire molecules. Yeah. Other questions? So we're going to talk now about some different types of intermolecular forces. So these are all intermolecular forces we're going to talk about. The first type of intermolecular force is what is referred to as a dipole-dipole interaction. And by the way, I guess I should mention this as well. All intermolecular forces basically work on a very simple principle of they work by positive and negative attraction. So the positive side of one molecule is attracted to the negative side of another. That is essentially how every different type of intermolecular force works. So when we talk about dipole-dipole interaction, that is when molecules that have dipole moments, and if you remember, dipole moments happen when we have what type of molecule? A polar molecule. So a polar molecule has an overall dipole moment. That means that overall the electrons are not being shared equally. There is a side to that molecule that's more negative and a side that is more positive. And that is perfect for intermolecular forces because you got a positive side and a negative side. So that's going to work really well. So basically, dipole-dipole interaction is basically the main force that holds polar molecules together with other polar molecules. And these are molecules that typically do not hydrogen bond, and we'll talk about what that is in just a second, but they typically do not hydrogen bond. And what that basically means is if you have a polar molecule, it essentially has a positive side and a negative side. And if you take another polar molecule, it also will have a positive side and a negative side. And right there between the two opposite charged sides of those molecules is where that interaction is going to happen and how they're going to basically bond together. Yes. Uh, Polar molecules do hydrogen bond, but dipole-dipole interaction is typically for polar molecules that don't have the ability to hydrogen bond. So they don't have the ability to hydrogen bond. Let me put that in there. Do not have the ability to hydrogen bond. And we'll talk about what hydrogen bonding is in just a second. But yeah, definitely polar molecules can hydrogen bond. But typically when we classify something as dipole-dipole, it's for those polar molecules that cannot hydrogen bond themselves. So for example, if you took something like, we'll do NF3 here. This is a polar molecule, right? It's one of those unsymmetrical geometries. It clearly does not have a hydrogen, which means it cannot hydrogen bond with itself. So this would probably use something like dipole-dipole interaction as its main sort of source. Now, these are only about 1% as strong as covalent or ionic bonds. And again, that's what we were just talking about. Covalent ionic bonds are intramolecular forces, which are much, much stronger. So here's dipole-dipole.
Atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So as we saw there in that little animation, something like SO2, another example of something that is polar It doesn't have hydrogen, so it cannot hydrogen bond. So its sort of intermolecular force would be dipole-dipole. As I also showed there in that animation, they do try to sort of move around, especially in the liquid phase, enough to maximize kind of the positive and negative sides being near each other and minimize the negatives and negatives being near each other and the positive and positives. No matter what you do, you are going to get obviously some negative and negatives near each other, some positives and positives near each other, but they will continue to sort of move around and try to find what is best really in energy and stability to sort of maximize that more attractive forces that occur between these guys and minimize the repulsion forces that would occur as the positive sides get near each other and the negative sides get near each other. Now, hydrogen bonding, which is what we were sort of talking about a little bit here. Hydrogen bonding is actually a type of dipole-dipole interaction, but it is usually classified kind of by itself. And it is, as the name implies, a bond between hydrogen and some other electronegative atom. In order for something to have the ability to hydrogen bond, you have to have hydrogen there, and that hydrogen has to actually be directly attached to one of those three elements, nitrogen, oxygen, or fluorine. So you got to have that hydrogen directly attached to one of those guys to be able to hydrogen bond. If you look at the periodic table, that three-pack there of nitrogen, oxygen, and fluorine, that is heading towards our most electronegative elements, right? And because of that, what that will create is a really big separation of charge, and that's going to allow a pretty strong attraction going to happen because you have a positive and negative guy. So for example, if we took something like methane, which has a load of hydrogens, can methane hydrogen bond? It cannot hydrogen bond even though it's got a ton of hydrogens. And that's for two reasons. First off, the carbon-hydrogen bond is actually nonpolar, right? And secondly, the hydrogens here are not attached directly to a nitrogen, oxygen, or fluorine. So even though it's got a bunch of hydrogens, it cannot hydrogen bond. Our friend water is attached. This hydrogen is attached directly to oxygen. This hydrogen is attached directly to oxygen. That means that water can definitely hydrogen bond. Water could hydrogen bond with itself, another water molecule, if you will. Again, through the positive side of the hydrogen, negative side there of our oxygen, and we get hydrogen bonding here that's going to occur. By the way, water could also hydrogen bond to other different molecules as well, like methanol. This is methanol, which has a nonpolar side, but also has a polar bond, very similar to what you see in water. And water has no problem interacting with this the same way. They will hydrogen bond the exact same way between those two. That's why something like methanol is soluble in water, because they can interact with each other using the same type of intermolecular force. So again, we can use these intermolecular forces between two of the same sort of molecules or multiples, or between one molecule and a different molecule that might allow them to interact well with each other. That is the basis of a lot of things in sort of solubility, is if these molecules are going to be able to interact with each other with the same intermolecular force that they use with themselves, they're going to be very, very soluble in each other. If you get two things coming together that basically interact with different types of intermolecular forces, they're not going to mix very well at all, because they won't be able to interact with themselves, with each other, because they're using different types of intermolecular forces. How about like ammonia here? Can ammonia hydrogen bond? The answer is yes. We have our hydrogen directly attached to our nitrogen. So again, something like ammonia has the ability to hydrogen bond. Something like HF also has actually the ability to hydrogen bond as well.
those three elements.
Some polar molecules have unusual.
Yeah, so in order to have the ability of the hydrogen bond, that hydrogen does need to be attached basically to those three elements. Again, because they're basically your most kind of electronegative elements.
Strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with two hydrogen atoms and two unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom. Hydrogen bonding forces are a tetrahedral arrangement of.
So this is what we were talking about actually earlier with ice. You can see all the big open spaces between the water molecules in this solid version that again basically swells ice, and it creates its density to be a lot lower than it is in liquid water, again because it's going to create a larger volume there. And as you can saw in the kind of the picture here, as it kind of breaks down into liquid, we lose those kind of areas.
Structure. In liquid water, the tetrahedral arrangement is not fixed because.
So again, you can see it kind of breaks down. We don't get all that big open space between them, and that's what actually brings, again, the density of liquid water actually higher than the density of ice because, again, they're able to kind of get closer to each other, a smaller volume that occurs in that case. All right. Now, the next type of interaction is dispersion forces. And dispersion forces are sometimes referred to as London dispersion forces. These are pretty much your weakest type of intermolecular force that exists among noble gases and nonpolar molecules. So dispersion forces are pretty much your go-to for nonpolar molecules. It is basically how nonpolar molecules interact with other nonpolar molecules. So why is that? Well, when you think of a nonpolar molecule, it is essentially neutral. And that is because it has equal sharing of electrons. So there is no negative side, there's no positive side there. And that's kind of bad in the sense of intermolecular forces because that's pretty much how you interact with intermolecular forces. You need a positive side and a negative side to come together. So they have to actually rely upon a couple of things that could happen. They have to rely upon what is sometimes referred to as an induced dipole. And what that means is if you have a nonpolar molecule and you bring, let's just say, a polar molecule near it, or even an ion near it, one of those two, what's going to happen in that nonpolar molecule is the electrons, for example, will go, oh, that's negative. I want to go this way and get away from those guys, right? Because they don't want to be near them. And what that's going to do is in this nonpolar molecule that normally doesn't have a charge or a separation of charge, it will temporarily gain a separation of charge as those electrons try to evade. And that will temporarily give it a way to interact with each other. This is, for example, like when you take oil and vinegar, right, salad dressing, and you mix it up. They're able to interact, right, for a period of time, but they can't maintain that interaction. They're going to separate out. It won't be able to basically maintain that interaction for a really long period of time. Now, another way that this could happen is what is sometimes referred to as an instantaneous dipole. And in an instantaneous dipole, what you have, for example, is, here, two nonpolar molecules. And neither one of them have any type of charge, but it is possible that all the electrons that are flying around, all the electrons could decide, for example, in this molecule to all take a vacation over here and go this way. And if they all decide to vacation together there on the left-hand side of the molecule, that is now going to create in this first nonpolar molecule a separation of charge that was not really there to begin with. And now it's next to this other nonpolar molecule, which is going to cause the electrons in this guy to be attracted to that positive side. And that's going to cause this second nonpolar molecule that normally doesn't have a charge to now pick up a charge. And now these two normally nonpolar molecules that don't have any type of charge has a way to interact with each other through the positive side of one and the negative side of another. This is temporarily because what will happen when these electrons decide to come home for vacation? That interaction is going to go away, right? And a new interaction is going to happen with some other ones, and that's going to go away, and it's going to kind of come and go, come and go. So these type of interactions, which are dispersion forces, are really the weakest you could get because they do have to rely upon something happening in order for them to sort of interact with each other. And that is different than, for example, when you have a dipole-dipole interaction or a hydrogen bonding interaction, and that is different because these guys have polar molecules. And the difference between polar molecules and nonpolar molecules is, for example, if you took something like water, no matter what you do to water, it always has a positive side, it always has a negative side. It doesn't need anything to happen for it to get those charges. It's good to go out of the gates, it's ready to interact, and it doesn't require anything to happen. The difference here between nonpolar interaction is it needs something to happen. It doesn't always have a charge. It needs something to occur for it to sort of gain that temporary charge for it to interact with one another. And that's what makes it really the weakest of all those interactions. And if you sort of arranged it in terms of what we've been talking about, hydrogen bonding, which is a type of dipole-dipole, is probably your strongest intermolecular force. Your weakest would be dispersion forces. So anybody that's rocking some dispersion forces is going to be the weakest. And really your dipole-dipole is kind of close to here as well. And again, dispersion basically are nonpolar molecules. Dipole-dipoles pretty much are polar molecules that don't hydrogen bond. And hydrogen bonding is our polar molecules that have the ability to hydrogen bond. And that's sort of the arrangement here. Now, when we talk about dispersion forces, it does increase in strength with increasing molar mass. So as the molar mass increases, when you're comparing dispersion forces versus dispersion forces, the strength of the dispersion force increases with the guy that has the higher molar mass. The only way you could get a higher molar mass is you probably need more elements or atoms, and more atoms means more electrons, and more electrons means there's a greater chance that those electrons could go one way or the other. And there's also a greater chance of more interactions occurring at different spots along the way. So when you're comparing the weak interaction to the weak interaction, dispersion to dispersion, the higher the molar mass, the stronger the dispersion force is. It's still weaker than any of the other two, hydrogen bonding and dipole-dipole, but there is differences in the strength of that weak sort of interaction because of those different electrons. By the way, instantaneous dipole is sometimes referred to as being polarizability, the ability of those electrons to kind of move one way or the next.
Solid carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical. leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So here's sort of the idea of an instantaneous dipole. Again, just based on electrons sort of separating, this guy gets a temporary charge, causes this guy to also gain that temporary charge, and then you get some interactions that occur between them. Now, when we talk about this, as I mentioned before, the hydrogen bonding is the strongest. It is typically for polar molecules that can hydrogen bond. And because it's the strongest interactions, these intermolecular forces affect things like melting points and boiling points and stuff like that. So typically, these guys that can hydrogen bond have high melting points and boiling points. They usually have pretty high ones because of that. Because it's a relatively strong attraction force, it takes a lot more energy to kind of break them apart. Dipole is the main interaction, as we talked about, between polar molecules that basically cannot hydrogen bond. And again, they would also have relatively high melting points and boiling points. Not as high as hydrogen bonding, but they would definitely have higher ones than, say, something that's using dispersion forces. They would have higher than this guy, which is dispersion forces, which is typically your nonpolar molecules interactions. And this is probably your lowest in terms of melting points and boiling points because they're not held together very strongly. That is essentially the intermolecular force dispersion forces that a lot of organic compounds like methane, propane, butane uses. If you think about those guys are typically gases under normal conditions, again, because they're not held together very tightly. Everybody could pretty much do dispersion forces, but it's not everybody's main route of interaction. So polar molecules can do dispersion forces, which is, like I said before, why things can mix for a little bit of time, like oil and vinegar sort of salad dressing. But again, at some point, if you just leave it alone, everybody will separate out from each other. There's no way to maintain that interaction. So something that is polar, interacting with somebody else that's polar, will use either dipole. Dipole is the main force, or hydrogen bonding as their main force. But technically speaking, they can dispersion force as well, along with everybody else. But nonpolar is pretty much restricted to just dispersion forces. Any questions on that? So this affects things like melting points and boiling points. It also affects things like I talked about a second ago, solubility. Again, things are typically going to be soluble in each other, as I mentioned before, if they're using the same type of intermolecular force that they use with themselves. So water works great with anybody that hydrogen bonds. If you try to do hydrogen bonding with water, something that's like organic, they will not mix together. And we saw that, for example, when we did those halogen experiment, right? We had the different layers in the test tube. The reason we had the different layers was the top layer was the organic layer, which is nonpolar and using dispersion forces. The bottom layer was the water layer, which is using hydrogen bonding. So they basically separate and can't always mix together. All right, so let's talk a little bit about vapor pressure that I apparently wrote all over. So I'm going to get rid of that there. So evaporation or vapor pressure is occurs at the surface of a liquid. So when we have evaporation or vaporization, that is when molecules really gain enough energy to escape the liquid phase. Requires a certain amount of energy to overcome these intermolecular forces. The process of condensation is when they sort of lose enough energy and they kind of fall back into the liquid phase. The pressure of the vapor over a liquid is basically the vapor pressure. So at the surface of any liquid, you have molecules jumping out and ones coming back in to the liquid phase. That is why, for example, if you spill a little bit of water on the bench and you leave it, eventually it will evaporate, right? And it will evaporate because you have the rate of evaporation happening, and you normally would have condensation coming back in, but there are air molecules that blow away those guys as they evaporate, and they're not there to come back into the liquid phase, and eventually your little pile evaporates off. Also why it takes much longer, right, if you put a liquid in a beaker, right, for it to evaporate away, because only the top guys are available there to kind of escape. You have a lot of this guy here take a much longer for it to evaporate. Also, it probably would not evaporate very much if you took a lid, right, and you put it on your container. That's going to escape or prevent the evaporation route from them leaving basically the container. So as this is occurring, for example, in a closed container, you will have guys jumping out and guys coming back in, but there will be some vapor or gas molecules from the liquid above it, and that is what causes vapor pressure. The weaker the intermolecular force, the greater the vapor pressure would be. And that is, for example, why something that's organic, as I mentioned maybe the other day, they are sometimes what are referred to as being volatile, which means they could go in the liquid phase and you open the container and they'll go into the gas phase really, really easily. And that is because they have a very high vapor pressure because they just jump out of the liquid phase. They're not held together very strongly. Things with very strong intermolecular forces typically will have a low vapor pressure because they're going to stay in the liquid phase and really not escape. And that's what we see here. If you ever look at a liquid in a container, you put some in. If you compare the liquid level at the beginning to when it comes to what's known as equilibrium, when you put a liquid in there at the beginning, you pretty much have a strong rate of evaporation happening. But because this is closed, those guys have nowhere to go, which means you will get some rate of condensation happening. And at some point, the rate of evaporation and condensation will equal each other. They'll jump out of solution, come back into solution at the same rate. And usually what that means is you lost some of that liquid up here, and you'll actually see a slight decrease in the volume of your liquid when you look at it. All those sort of vapor molecules above the liquid is what causes the vapor pressure of that liquid. And again, the more gas molecules you have above the liquid, the higher the vapor pressure you would have. The less gas molecules, the lower the vapor pressure. And again, like I mentioned, if you have a really strong intermolecular force, it's going to be much harder for those guys to escape the liquid phase and go into the gas phase versus somebody that has a weaker intermolecular force. They're going to be able to just jump out of the liquid pretty easily. You'll have a lot of gas molecules above the liquid and a high vapor pressure. Any questions on that there? Yes. No, evaporation is really the process of a substance going from liquid to gas. Vapor pressure is the result of how much of those liquid molecules basically got into the gas phase and are kind of stuck above the liquid is typically what that means, yeah. So there's one sort of the action of it happening, the other one sort of the end result of it happening in a sense in terms of the vapor pressure. Other questions? All right, well, we'll wrap it up for